morning, everybody. Welcome to Dev Days 2018. I hope you all have a lot of fun. I like the theme of the conference. We're all here to be inspired, right? And one of the things that inspires me is just the profession. I think it's a wonderful thing that we do for a living. And I think one of the nice things about a keynote talk is to try and be inspiring and try and talk about broad concepts. So my topic for this morning is to talk about software engineering and particularly kind of taking back ownership of the idea of software engineering. And that's really what my theme for today. As the introduction said, I've been working in software industry for a very long time now. And when I started out, I often had job titles like junior software engineer and a software engineer and senior software engineer. I think I was a principal software engineer once in one job or other. And if I'm honest, during those times, I did nothing that was even close to engineering. And then for a period, I worked in a series of companies where the term software engineering kind of got a bit of a bad name. And we didn't really like the term software engineer anymore. And we talked about ourselves as being software developers. And sometimes we talked about ourselves being craftspeople. And we thought of ourselves differently. And then later on, more recently, I did some work where we genuinely started doing some engineering. We genuinely started applying what I think of as engineering principles to the job of software development. And as you might expect in terms of applying engineering thinking, it worked really well. And now I've started to think myself again as a software engineer. And so I want to talk about that idea a little bit and describe that. And I think in part, one of the reasons why software engineering and software development got a bad name is things like this. So this is a diagram, and certainly when people talk about software engineering, this is one of the things that kind of springs to my mind. This is to software engineering what a soldering iron is to electrical engineering. It's a tool. It's not software engineering. This doesn't define engineering as a practice. And there are other kinds of tools. We can think about the processes that we work on. And this too, sometimes this is thought of as an engineering discipline, but it's not. Has anybody any idea how many times the documentation for Scrum, of which this is a diagram, very good project management process, but the documentation, how many times does it mention the words software or code? None. It mentions those ideas 0 times. So this is not an engineering discipline. If we're not talking about the stuff that we're really doing, it can't be an engineering discipline. So this isn't really answering the question either of what software engineering might be. As I mentioned, in later years, we started talking about the idea of software craftsmanship. And I think in many ways that was a reaction to some of the kind of big, heavy disciplines that polluted our industry through the late 80s and early 90s, and were problematic. And in reaction to those, agile came in and started changing the way that we thought about those and introduced ideas like craftsmanship. I think there are good reasons for that, which I'm going to explain why I think that's a thing. But this too is not really about software engineering. It's a different kind of thing. Craftsmanship, craftspersonship, it brings a different set of qualities to what it is that we do. One way of thinking about this is to think a little bit about the history of production, of human production of things. And for tens of thousands of years, all human production was really based on craft. It wasn't an engineering discipline as such. It was individually handcrafted things were the only things that we created. And then roughly at the middle of the 19th century, we started ideas of mass production. That was one of the first events for which mass production came to the fore was a war. It was the American Civil War, where they used mass production techniques to build the rifles and armaments that made that war such a terrible thing that killed so many people. There's an interesting story about that. If you can have an interesting story about such a horrific time, there's the man that wanted the contract for selling armaments to the northern states in America went into Congress with a bag full of components of rifles, and he tipped the bag out on the floor. He got the congressman to select the components from the floor, and then he assembled a rifle from all of those pieces. That was the first time in human history where that was possible. Before that, if you wanted a rifle, you went to a gunsmith who built you a rifle. It was an individually handcrafted, tailor-made piece of machinery. And it was unique. The tolerances were different for every rifle. When you got your rifle, it came with a little mold that gave you the bullets that fitted in your rifle, nobody else's rifle. And so standardization was an important step forward in the progress of being able to make things. At the end of the Second World War, in the 20th century, lean production techniques came in, and they kind of started applying more scientific rigor and more scientific thinking to the process of making things, and they had a deep impact on the manufacture of things. Most modern production companies that make things use lean production techniques because it just works better, it's more efficient, it's more effective. So let's just explore those three ideas in a little bit more detail. So craft-based production techniques, it's about art rather than science. It's about the talent of the individual craftsperson and the skills that they can bring to do the work. There are no standards in the work. Each piece of work is individually handcrafted and unique as a result. And it's based on individual expertise, how good that is. I think that we have an emotional reaction to the idea of craft-built things. We like, if we're very wealthy, we like hand-stitched leather in our cars and so on. But in reality, craft-produced things are lower quality than manufactured things. For a moment, just consider a craft-built one of these. It doesn't make any sense. You couldn't build a device like this using craft-based technologies. It doesn't make any sense. Even the prototype for this needed heavy engineering and industrial power to be able to create something this sophisticated as a starting point. So that's not the answer either. Mass production came along and it brought in ideas of assembly lines, standardization of components, standardized steps. Effectively what you do is you build out a whole bunch of pieces, components of stuff, and you kind of push them down the line towards completion, and from which you can assemble cars or rifles or whatever it is that you're building. It's kind of a push-based system. One of the big differences between it and the next innovation in production, lean production techniques, is that lean production is a pull-based system. It brings in ideas like just-in-time manufacturing, just-in-time delivery, just-in-time warehousing. Instead of pushing things down the line and building up a large inventory of stock, you pull things just in time, just when you need them, and then you assemble whatever it is that you're trying to build. And it brings in ideas like one-piece flow, minimizing work in progress, and so on. So where is the software industry in these? It's not really, it's not a clean fit with any of those things, but they're good analogies. Another way of thinking about this that's kind of interesting is this. One of the fields of expertise that are very expert in managing processes is chemical engineering. The nature of their job is to analyze different kinds of processes and to automate those. And so, unsurprisingly, they have a taxonomy for processes. And this is one example of chemical engineers thinking about process control models. So this is the defined process model. The defined process control model requires that every piece of work be completely understood. Given a well-defined set of inputs, the same outputs are generated every time. A defined process can be started and allowed to run to completion with the same results every time. I don't think that sounds very much like software development. If it was that simple, if it was that straightforward, then once we'd built one web system, we'd be able to just press a button and generate all of them. It's not that straightforward. For us, our problem is different. It's profoundly different from most different disciplines because our problem is not one of production. Production for us is we press a button and the compiler whirs or a build system whirs and we've produced the thing. Our problem is one of design. Our problem is one of exploration of a problem space. It's a different kind of problem. For this process control model, this is the world where our ideas like mass production, assembly lines, and waterfall processes make sense. These are what's required. We can have reproducible results every time. Another one of the chemical engineers' process control models is the empirical process control model. The empirical model of process control provides and exercises control through frequent inspection and adaptation for processes that are imperfectly defined and generate unpredictable and unrepeatable outputs. To me, that sounds a lot more like software development. That sounds a lot closer to the discipline that we are all engaged in. This is the world of craft-based production. Craft-based production fits well for these kinds of models. It's about exploration, it's about continual improvement, and it's about lean process. I think this is one of the reasons why the software crafts movement gained ground, because it's a better fit than the traditional kind of heavy waterfall plan-based approaches, which are better, a better fit for production-driven problems. So where are we in the software industry? I think that we are nowhere close to mass production, and we never will be. That is not our problem space. That is the wrong kind of solution to the kind of problems that we face. Our problems, as I said, are about design. I think that we are here. I think that we are a craft-based industry. I think if you look at the distribution of success in software teams, the variation in quality between the best and the worst is huge. That's the kind of thing that you see in craft-based disciplines, not in engineering-based disciplines on the whole. There's little standardization and predictability in approach. I think that where we should be aiming to be is here. I think we should be shooting to try to get towards more lean production and learn from the lean manufacturing movement and apply that kind of thinking to software development. And agile processes are a good step in that direction. They don't take us all of the way. When we get this right, what we see are quite dramatic changes in the performance of software development. We see enormous speed-ups in terms of the rate at which we can develop change. We see dramatic changes in the efficiency of software development teams in terms of the amount of time they spend doing new work versus remedial work, fixing problems that they introduced. And we see, significantly, that organizations that practice these kinds of disciplines make more money than organizations that don't. This is the first time that we've ever, in the history of our industry, had data like this that says that if you practice this kind of engineering rigor in your approach to software development, your organization makes more money. I've been talking about this kind of thing for a few years now, and I get involved in conversations with people at different times. If you stop me in a bar or something like that, I'll probably bend your ear about continuous delivery and engineering and those sorts of ideas. And one of the things that kind of surprises me is the amount of conversations I have about bridges. What I tend to say, I was talking about software engineering, and usually the pushback is, yeah, but what we're doing is not bridge building, is it? And it's not. What we're doing isn't bridge building. But then, fairly typically, as a software, one of the failures of us as software developers is that we tend to assume that everybody else's problems are simple, I think, sometimes. Bridge building isn't what we think it is either. If you are building the first kind of a bridge that's never been built before, that's a very different kind of experience to building the millionth bridge of a certain kind, or the 1,000th bridge of a certain kind, or even the 10th bridge of a certain kind. The 10th suspension bridge was a lot simpler to do than the first one. The first metal bridge was an incredibly difficult problem to solve, an incredibly difficult problem in design, and after that it was easy, because we kind of solved a lot of the problems. As I said, our problem is a design problem. So we are always building the first bridge. The other thing that's true about this is that software engineering is not the same in different disciplines. Bridge building is not the same as house building. It's not the same as engineering in aerospace, which is not the same as chemical engineering, electrical engineering, rocket engineering, space engineering, and all of these things are distinct. So I think that one of the things that we can be certain of is that anything that we can genuinely call software engineering is going to be unique to us. It's going to be our thing, and it's going to be distinct from other forms of engineering. The other way in which engineering is not always the same is at scale. Here are two engineered structures. It's evident from looking at these that the level of engineering that went into each is very, very different. You can bet if this was a shed that was built by IKEA, there would have been a lot of work that went into making sure that you were using the minimum amount of wood and it came to a price and all of that kind of stuff. But even then, that's going to be engineering on an entirely different scale to this, which is the tallest building in the world, the Burj Khalifa. The engineering that went into this thing would have been leading edge. They would have been doing computer modeling and wind tunnel testing with models and finite element analysis, all kinds of things to engineer a structure like this. For something like a building, this is absolutely evident. For something like software, not so much. It's not so evident necessarily that the engineering that goes into writing some software for my mum's cake shop is different to the engineering that goes into or should go into developing software for a driverless car or a medical device. But it will be, and it should be. So engineering changes in terms of the discipline and in terms of the scale of the thing that we're going to do. But there should be some common themes. If we're going to talk about engineering and apply that, well, there should be some common themes. As I've said, I talk about engineering a fair bit. And from time to time, I get involved in conversations on Twitter about this. And this is one that I've sent to me. I've kind of hidden the sender of this tweet because I strongly disagree with this. So for me, engineering means working in a certified inflexible process that includes planning ahead a lot, the antithesis of agile. I'm sorry, but I think that's absolute nonsense. If you look at something like the Curiosity rover, the engineering that went into that, it wasn't working in a certified inflexible process. It was groundbreaking innovation and creativity. That's what we're talking about. And that's our discipline. Every time that we write some software, it's going to be innovative. Otherwise, why would we bother? If it was the same as we'd done before, we'd just press the button and we'd use what we did before, because production is free for us. So it's always going to be this exercise in discovery. So these kinds of pushbacks shouldn't get in the way. So let's start digging into this. Let's start thinking about what engineering really is. And here's Wikipedia, the speaker's friend in terms of definitions. So engineering is the application of mathematics, empirical evidence, scientific, economic approach, practical knowledge. There's all of these words, these kind of crop up over and over again in the definitions of engineering. Some more definitions. The science of making a practical application, and so on and so on and so on. And the application of scientific and mathematical principles to practical ends. The same words tend to crop up. So here's my working definition. This is really what I have in mind when I'm talking about engineering. Engineering is the application of empirical scientific approach to finding efficient solutions to practical problems. If you've read any of the work of David Deutsch, I think this is what he would call a good explanation. It's hard to take away any of these words and leave the explanation intact. You don't really need to add any words to understand what it is that we're talking about. So this is a reasonable explanation of what it is that we're trying to shoot for if we're trying to get a definition of engineering in our discipline. And for me, there are 5 properties of what I would think are fundamentals of anything that we could deem to be an engineering approach. First, it's going to be iterative. Second, it's going to concentrate on the application of feedback and give us an opportunity to learn. It's going to be incremental. We're going to build systems incrementally, piece by piece. It's going to be experimental. We've got to learn and adapt as part of the process. This is fundamental to our ability to create and evolve the designs of our systems. That's how we really build clever systems. You never build a clever system by getting it right first time. All complex systems start off first as a simple system and then evolve. And last, it's going to be empirical. We're going to have to measure this against the real world. So let's dig into those in a little bit more detail. Iterative. Iteration is the act of repeating a process. Iteration is the act of repeating a process, and the bit that we're interested in is with the aim of approaching a desired goal, target, or result. Iteration is important because it means that we can learn, react, and adapt to the things that we observe. It gives us an opportunity to evolve our thinking and work over time. It allows us to steer towards a goal. I think one of the innovations of agile development processes was to allow, at the project management level initially, was to be able to steer the project towards a more successful outcome. I think we can take that kind of thinking and apply it more deeply to other parts of the process. And to be fair, some of the early agile processes like extreme programming did that. It allows us to have this approach of continual improvement. We can refine and improve the things that we create and make them better over time. And it allows us to practice important aspects of our work so that we get better and better and better and better at things. This is one of the fundamental importances of the application of an iterative approach to software development. Feedback. Feedback is information about actions returned to the source of the actions. Feedback it allows us to observe the impact of our choices. We can reflect again what's going on and allows us to steer better. My favorite approach to software development is unsurprisingly based on the ideas of continuous delivery, and this is the model that I use to try and explain continuous delivery people when I'm teaching them about it. This is a high-level abstraction, but it's kind of a schematic of the feedback loops that are inherent in a continuous delivery process. Have an idea, get that idea into the hands of users, and figure out what they make of it, and in the middle you use test-driven development and those sorts of techniques to move very quickly and other kinds of feedback. But feedback of all kinds is absolutely essential to our ability to learn and evolve evolve our understanding over time. We want our development approach to be incremental. Incremental is about evolutionary design, continuous design, evolutive design, and it's directly related to modular design, interestingly. So my wife, who's sat over there, says that I'm a serial nerd. And she's wrong, because I'm actually a parallel nerd, because I can be a nerd on multiple fronts at the same times. And one of my nerdisms is I'm interested in aviation and the space program. So I'm going to do a little bit of parallel nerdism and give some examples of software engineering or engineering using the space program. So this is a picture of a Saturn V. This is still the largest spacecraft that human beings have built so far. Elon Musk is planning on a bigger one, but he's not built it yet. This was built in the 60s, and this was the thing that took people to the moon. This was the first time that we did this, and this was a highly modular system. This is one of the hallmarks of the Apollo program. This part of the spacecraft was about getting the rest of it from Earth into Earth orbit. An enormously complicated job, lifting all of that mass out of the grip of well, not out of the grip of gravity, but into orbit. The top part of the spacecraft was broken up into a series of modules as well. This is two of those modules. This is the command module. This is the bit that was the job of this was to get the astronauts from Earth orbit back down to Earth. And this part, the service module, its job was to be the vehicle that took the spacecraft from Earth to the moon and from the moon back to Earth. And then there were some more modules. There was the lunar lander, and this itself was in two parts. This was the lunar ascent module, which took the astronauts from the moon back into lunar orbit, and this was the descent module, which took the spacecraft from lunar orbit to land on the moon. If it wasn't for this modular approach had a number of benefits. It meant that different organizations in the American aerospace industrial complex could be concentrating on different parts of the spacecraft. Different companies built different parts of the spacecraft. It meant that when bad things happened, like Apollo 13, when part of the spaceship blew up, they were able to reconfigure the system and use them in unplanned ways, because it was more flexible, because it was modular. The astronauts ended up using this part, the top part of the spacecraft as essentially a lifeboat to bring them back to Earth. Modular systems are important for another reason. It allows us to do, in technical terms, in lean technical terms, it allows us to reduce the batch size. It allows us to work in smaller increments and allow us to make progress in small steps. And that's very healthy, because that's a key step in reducing risk. It's much more risky to release large, complicated changes into production than it is to release a series of small, simpler changes that are well thought about and tested. If something goes wrong with the small, simpler changes, It's easier to back them out. It's easier to understand what went wrong. And all of the data says that if you go fast with many small changes, you create higher quality work more quickly, more stably. There's lower risk than if you're going more slowly, creating larger changes with larger releases with big changes. I've mentioned two words that are kind of very close in the English language, iterative and incremental. And the best description of the difference between the two that I've seen, I've stolen from my friend Jeff Patton, who included this in his book on story mapping. Iterative is this. So you're going to kind of do a sketch of whatever you want, and you're going to fill in detail over time. Incremental is this. This is the modular thing. We're going to realize a module, and we're going to do that. We need both of these kinds of thinking. If we're going to apply engineering discipline to our software projects, we need to apply both of these kinds of ideas. We need to be both incremental and iterative if we're going to succeed. Experimental. An experiment is a procedure carried out to support, refute, or validate a hypothesis. Experiments provide insight into cause and effect by demonstrating what outcome occurs when a particular factor is manipulated. I would argue that this kind of reasoning is the difference between the success of humanity in the last 200 years, the high-tech industrial global civilization that we have, compared to essentially a largely craft-based agrarian civilization that preceded it. It took us tens of thousands, hundreds of thousands of years to learn this lesson, to start applying this kind of thinking to solving problems. I want to tell you another little space-based story to try and make my point. In 1961, the American president, John F. Kennedy, stood up in Congress and said, we're going to send a man to the moon by the end of the decade and bring him home safely. And everybody in NASA, when he said that, went, because they had no clue how to do that. At this point in history, this was 2 weeks after Alan Shepard, who was the first American in space. The Russians had been there first. But the first American in space, Alan Shepard, he was an incredibly brave man. At this point in history, the American space rockets were blowing up all of the time on the pad. They were failing regularly. Essentially, Alan Shepard was strapped on top of an intercontinental ballistic missile in a tin can, shot 60 miles up, and then parachuted back down in the tin can. 2 weeks after that, Kennedy's saying that within 9 years we're going to land people on the moon. And nobody knew how to do that. So he's just kind of set this goal. He's painted this vision for what's going to happen. Somebody once said, is this the most expensive user story ever? I think it might be. I think it's in with a shout. He's kind of painted this vision. And here are some pictures of all of the things that NASA didn't know how to do at the time, which is basically all of the things that you need to know how to do. So at this point, they hadn't got launches set up. If you ever see a film montage of this period in space, in rocketry, in American, their rockets are blowing up all of the time at this point. They hadn't got multi-stage vehicles working yet, and the separation. They hadn't got the splashdown working yet. The next American to go into space, Gus Grissom, when he landed, his capsule sank, and they lost the capsule. Nobody had docked two spacecraft together. Nobody had done a spacewalk. They hadn't really got the mission control stuff sorted out. All of this stuff was stuff to learn. So where do you start? You're given this monumental problem. Where do you begin? One of the ways in which you begin is that you hire really smart people. This is Margaret Hamilton. This is the first software engineer. She's credited with defining the term software engineering. She invented the term for the first time, and this is some of the code that she was in charge of the software development for all of the flight systems for the Apollo program. In particular, she wrote the systems that saved the actual lunar landing when it shed load and allowed the software to concentrate on its critical functions. But where do you start? So a good place to start is to think about the problem. And here's a picture of the Earth-Moon system, except this is a kid's storybook picture of the Earth-Moon system. This isn't really the problem. This is the problem. This is to scale. And at this point in human history that we're talking about, no human artifact had been more than 1 pixel away from the planet Earth. So problem 1, how do you get anything from here all the way over to here? How do you do that? You can kind of imagine the conversation going in NASA the day after Kennedy stood up and spoke about it. And they go, oh, what do we do now? Well, my cousin Joe's got a car dealership. We could go and get jobs there. No. Well, I know. I've got an idea. Why don't we build a spaceship, put 3 astronauts in it, send it to the moon and see if they come back? No, not really. That's not really a great idea. What we could do is we could build the spaceship and send it without the astronauts. Let's just build the spaceship, send it to the moon, see if it comes back without the astronauts. That's better, right? Yeah, but it's still so hard. That's what's called big upfront design. That would be the waterfall approach to a space program. Well, that's not really what you do. So. How could we make this simpler? I know, I've got a great idea. Why don't we just build a spaceship, send it to the moon, and land the spaceship on the moon, not bring it back on the first go, and then we'll learn how to do that first bit. That's good. That's a great idea. That nearly halves the problem. It's a much simpler problem to not bring it back, so that's a good step forward. What does landing mean? It doesn't have to survive the landing. And that's where this program came in. This is the Ranger program, and the job of the Ranger program was to use spaceships as bullets to see if we could hit the moon. That was it. We're going to fire these spaceships, see if we could hit the moon. That was the job. How did that go? Well, the first Ranger blew up on the pad. I told you the rockets weren't great at that point. The second Ranger blew up on the pad. If you've ever worked in a large project, you might find the next bit funny, because the job of these 2 programs was just to get the Ranger into Earth orbit, and they both failed. But the program said, well, we're getting behind now, so let's just go ahead and let's go for the moon. So Ranger 3 got the spaceship into Earth orbit. It did the deorbit burn, shot off towards the moon, and missed it completely. Ranger 4, it worked. It got into orbit. It did the deorbit burn, but all of the systems failed. The spacecraft just died on its journey towards the moon, but they managed to track it from ground-based stations, and they saw that it did hit the moon. So that was a success of a kind. Ranger 3 missed the moon again. Ranger 5 missed the moon. Ranger 6, it worked. It hit the moon, they got telemetry, but the cameras failed, so they didn't get any pictures. Ranger 7 was a success. 8 was a success, and 9 was a success. So you're NASA in the Cold War with a budget to try and beat the Russians to the moon. You've got access to some of the finest engineering talent in the world. Can you just imagine being on the end of the phone and say, hi, it's NASA here, we're a bit stuck, we'd really like your help? You'd go and help, wouldn't you? We're trying to send rockets to the moon, could you help? I'd be there like a shot, I'd be on the next aeroplane. What do you do under these circumstances? You break the problem down into small steps, more small experimental steps. That's how we solve hard problems. That's how we solve any hard problem. We don't solve the hard problem by building the whole thing and then seeing if it works and crossing our fingers and hoping. There would have been millions more experiments than I've described here. There'd have been experiments on tension that breaks a bolt and all sorts of things. But the philosophy, the approach, the fundamental idea of trying things out and trying to figure out how to work is really what made this work. I want to do a little experiment. Have people seen this before? So this is a little test of experimentation. The idea is for you to determine which is the larger orange blob. Is that blob larger, or is that blob larger? Could you give me a show of hands? If you think that orange blob is bigger, can you put your hand up, please? Not very many people. If you think this orange blob is bigger, can you put your hand up, please? You've seen this before, right? So put your hand up if you think that they're both the same. Okay, good. So you've seen this kind of thing before. So here's another one. So here's an experiment. You can't really tell until you carry out the experiment. Here's my experiment. I've put some parallel lines in, and the blobs are in fact the same size. Now we know. Here's another one. Have people seen this one before as well? Yeah. So put your hands up if you think this line is longer. Put your hand up if you think this line is longer. Put your hand up if you think they're both the same. I'm sorry, you weren't paying attention. You have to do the experiment. This line is longer because I made it longer. You can't tell by guessing. Engineering is about measuring things. It's about figuring out what's really true and what's really not. We've got to measure things. Empirical, the last of my 5 crucial properties. Based on, concerned with, or verifiable by observation or experience rather than theory or logic. Theory and logic are vastly important. It's really important to build theories and to make explanations and then to be able to test those explanations. That's the scientific method. That's what engineering is really about, the practical application of those sorts of scientific principles. But theory is only theory until we can go and make a measurement in reality. We need to use measures of reality as well. This is really important. Being empirical allows us to be evidence-based. It allows us to separate out our beliefs from facts. It allows us to start applying a little bit more science into the way in which we work. We can never, ever be certain of success. We can, however good our theory, might be wrong until we try it out, until we test it against reality. Progress only comes, in fact, when we risk failure. In fact, the most valuable experiments are the ones that fail because that's the point at which we learn. If we make a prediction and say, I think that this works like this, and then the experiment verifies our prediction, we haven't learnt anything new. Maybe our experiment was bad, maybe it was good, we don't know, but we certainly haven't learnt anything new because all it's done is reinforced the idea that we already had. If we carry out an experiment and the experiment fails, you go, that's not what I expected. Now I've got to really think. Now I'm going to learn. So risking failure is essential. We learn most when reality does not match our predictions. Being experimental and allowing for that failure is fundamental to really making excellent progress. Production is always going to surprise us. That's not a bad thing. That's just reality. That's just a fact. And I think it should. That gives us the opportunity to learn and adapt. One of the ways that I came across this later, and it felt like a nice idea to me. If you think of all of our design choices, all of the documentation, the code itself, the tests that we have, our understanding of the problem, the requirements, the stories that we have that describe it, everything, the ideas in our head, all of it really is only our best theory for what's true at the moment. And we should be always striving to improve our theories. To give you a little analogy from science, one of the most beautiful theories in physics is general relativity, Einstein's idea of bendy sheets of space-time that explain how gravity works on a cosmic scale. It's a wonderful idea, a beautiful idea. And yet, at some level, we know it's wrong, because it doesn't match with the other kind of weird, amazing, powerful predictive tool of quantum field theory. They don't match up. And so there's something wrong. Both of them are probably a bit wrong, but they're the most accurate predictive tools that we've ever come up with. There are teams funded all around the world to try and dig into those and prove those things wrong, despite them being the most accurate ideas that mankind has ever come up with. That's how we should start thinking about our software. We should never assume that we know it all, that we've got it right, that it's finished. We're always learning, we're always iterating, we're always improving, continually. So it's only our best theory to explain things so far. So where do we stand on this? So the fundamentals of an engineering approach. I want to start applying that to my favorite development process, continuous delivery, as an engineering discipline. So it's iterative, it's deeply iterative, it's profoundly iterative. The idea of a deployment pipeline is to allow us to move very, very quickly and get great feedback on our changes, both at every level, technical, organizational, in terms of the product evolution itself. It's incremental. It allows us to build up step by step as we go. It's deeply experimental. We talk about optimizing the process from idea to getting useful software in the hands of users and figuring out what they mean. So that's carrying out experiments at the level of the product itself, but also at the levels of writing an automated test to try out whether my software works. It's empirical. We're going to go into production regularly, ideally multiple times per day, so that we can learn really quickly and understand what really works with users and technically and so on. It uses short feedback cycles, test-driven development, automation, hypothesis-driven development, test as a falsification mechanism. It uses these feedback channels that we've talked about. I think that continuous delivery is grounded in this. And if you've been paying attention to what I'm talking about, it'll be obvious what this is, even if you haven't seen this picture before. This is essentially a picture of the scientific method. We're going to make an observation, and from that observation of the world, we're going to propose a theory. And then, based on that theory, we're going to make a prediction. And then we're going to figure out a way of testing that prediction, and that's going to inform our observations. And we're going to go around in a circle. That's the thing that moves us from being an agrarian society to being the high-tech civilization that we all live in. Everything that is about us in this room is the function of that kind of thinking. And yet that's not the kind of thinking that typically we've tended to apply to software development. So software engineering as a discipline, we've learned over the years that in order to create good software, we don't treat these things as discrete steps. These are continua. We need to be doing all of these things all of the time. We're going to iterate through this process continually. And we're going to try all of these things all of the time. We're going to do these things all the time, every day. That's the best way of us, that's the most effective way of working. There's good data to demonstrate that. This gives us a lot of opportunities. It means that we can look to measuring these things. We can measure things like cycle time, how quickly we can go through the process, which is a decent proxy for the efficiency of our processes. But profoundly, it allows us to be more experimental. It allows us to have a theory, make a prediction, carry out the experiment by taking the software out into the hands of our users and understanding what they make of our ideas. We can have a theory and make a prediction and carry out an experiment technically as an automated test as part of our development process. All of this gives us an opportunity to learn. Fundamentally, I think that continuous delivery is an engineering discipline, and that it's not the only way in which you can do this sort of thing, but I think when we start applying this kind of engineering thinking to our software development practices, it gives us a profound improvement in the process. I'm coming to the end, and one of the pushbacks that I sometimes get is that the proponents of software craftsmanship say, "Yeah, but Dave, the craftsmanship's really important. It enhances skill and creativity and freedom to innovate, and it allows us to have these apprenticeship schemes, all of these great things." And I agree. These were really important things, and the software craftsmanship brought these ideas to the fore. But these ideas don't go away if we start thinking in terms of engineering. This is just as true as of an engineering discipline. Engineering is also an intensely skillful activity. It's deeply creative, particularly when we're talking about the kind of design engineering that is the fundamentals of any kind of software engineering that makes any sense. It gives us this opportunity to learn and adapt and innovate, and yes, we should be using apprenticeship schemes to learn the deep, challenging, difficult skills of being able to evolve complicated solutions and carry out experiments in our software in order to be able to create systems. Engineering adds to craft. It improves the repeatability. It provides guidance and structure when we're lost. It improves the quality of the output of our systems. And it improves the efficiency of our development process. All of this is based on data that we can measure through analysis of software projects. It gives us an approach to solving problems when we're stuck. You know, we come to a problem, oh, what do we do now? Well, what are we observing? So what's our theory? What comes next? If that was the case, what could we predict? And how would we test that prediction? It gives us a way of moving forward based on fact rather than just guesswork. So, in conclusion, I'm not trying to tell you to be like engineers. This is not an analogy. What I'm trying to advise is to be engineers. Start applying a little bit of scientific discipline into the way in which we start developing our software. Start testing things, start experimenting, start actively thinking about how you can apply scientific principles to your work, to every aspect of your work. And when you do, I guarantee that you will see a more effective result. Thank you very much. I hope you have a great day.